is 32, you look it up, tell me, I forgot, 32 degrees API, heavy crude, also has sulfur, which makes it lower quality, not suitable for all refineries and stuff. Anyways, to get API gravity, which is a calculation of this equation, you need to measure SG. And this is the simplest experiment in this lab. This device here is a floating device. What happens is you pour oil in a beaker or in a cylinder and just dip it into there and let it float. And it's graduated. Specific gravities, C fractions of 1 going from 0.800 to 0.900. So the surface of the liquid will be somewhere in between, and you just read that value right off the graduated floating thing. I even forgot what the term is. Hydrometer? Hydrometer. You just read the value, you write it down. I think you will be provided several different oils, vegetable oil, sunflower oil, corn oil, I don't know. Yes, water too. And yeah, just read it off. That was the fastest lab as far as I remember. Okay, so that takes care of the API or specific gravity, which is basically the same thing, right? Surface tension? And capillary pressure. We have 2 more to go in this room. I think it's cut out. The next one up here is an apparatus for measuring capillary pressure. What is capillary pressure? That's the petrophysics instructor's job to explain that. But basically, whenever you have 2 immiscible fluids, like oil and water, for example, or oil and air, side by side interfacing with each other, right? Like, for example, in a pore, let's say you have, let's say this will be rock, and this will be 2 pore spaces, and this is a pore throat. And let's say you have an interface. This will be, let's say, water, and this darker stuff will be oil. Okay? Did we talk about wettability in the lecture? We didn't, right? I think they cut it out of the lectures. I don't know for what reason. I think they left it for the petrophysics course because it created problems in tests. I don't know. It's an easy concept to understand. You know, everybody has polished cars, right? Why do we polish cars? So the cars, the paint repels liquid, right? It repels water to avoid corrosion and stuff like that. So if you have a solid surface and drop liquid of a drop of water, it will spread out like this, right? Okay? But if you drop on a Teflon surface, you drop like some liquid, let's say oil, I don't know. It will beat up, right? The way these droplets work is because of a phenomenon known as surface tension. Because why should this droplet even remain this way? Because there's weight pulling down. There's weight pulling down. So, and fluid can resist any shear stress. So it should just, according to the laws of physics, it should be spreading infinitely until it reaches, until you have a layer only 1 molecule thick, right? It should just spread out and keep spreading out until you have a layer of water 1 molecule thick across a large area, right? But that's something that doesn't happen even though the weight of the liquid pulls down. So if it stays lifted up like this, there should be a force pulling up. This force is called surface tension. This is the surface, and the tension acts like this. Oops, sorry. It pulls in this direction, right? There's an angle here called contact angle. Now, resisting surface tension, what surface tension is resisting is the adhesion force, because this surface, if it likes this fluid, it wants to pull it towards itself. There's an adhesion force pulling in this direction, in the opposite direction. Okay? And this is repelled. So contact angle here, if this is water and this is rock, this rock will be called water wet. Because it likes water. It wants water towards itself, okay? If this is water and this surface repels it, the angle will be greater than 90 degrees, okay? The contact angle will be greater than 90 degrees, and that means the rock here is not water wet, it's oil wet, okay? If this is water, then it's oil wet. I'm going into too many details, right? How am I doing on time? What time is it? 12:17. We need to wrap it up because we're on. Yeah, we need to wrap it up. Okay. Because of surface tension, we have capillary pressure whenever two immiscible fluids are interfacing with each other, okay? Capillary pressure, the term capillary pressure comes, has anybody had a blood taken from a finger? Like when they, right? What do? They bring a capillary tube and blood runs right into it, even though there is no pump or a suction device at the other end. There must be a force sucking it in. Because capillary is like, well, all capillary tube is just like a small diameter tube, very small diameter tube. And if you dip it into liquid, it will suck it right in, and the fluid level will rise in the capillary. Okay? This height here will be referred to as capillary rise. Okay? So there's no pump or no suction device here, but that's what capillaries do. And if you think about it, pores are also capillary because they're very small diameter. Any tube or something like a tube that has a very small size, diameter, will act in this way. So there's always a pressure difference between two interfacing fluids whenever there's a capillary present, okay? And if they're immiscible. Pressure in a non-wetting fluid, and we're going to be assuming that our reservoir is water wet. Pressure in non-wetting, pressure wetting. Capillary pressure is defined as the pressure difference between non-wetting, pressure in the non-wetting phase, and pressure in the wetting phase. And in our case, with a water-wet reservoir, it will be PO, P oil minus P of water. Okay, now, why do we need this thing? First of all, how do we determine capillary pressure in an experiment? Basically, we do the same thing as in the relative permeability experiment. We saturate a pore with brine, or saline water, and we start expelling it with gas, right? Okay? We're recovering with air. We're recovering liquid. We're recording the volume of the liquid. This is the same kind of deal. You have a core holder. You have pressurized gas, air in this case, feeding into the core holder, and you're expelling liquid and collecting it here and measuring volume. Now, what are you going to be plotting in this experiment? You'll be gradually increasing pressure, okay? And you start, on the x-axis, you have water saturation, which is, in the beginning, is equal to 1. You're going to saturate a core sample to 100% water saturation. And then, you're going to start increasing pressure. Pressure will be on this axis, on the y-axis. So, the curve will look something like this. You will have entry pressure for gas to enter the core sample, and then it will behave depending on the rock sample and the nature of the rock. It will behave in this way. Okay? This is the shape that ideally you will get in a nice porous and permeable core sample. What does this physically mean? In this direction, what do we have? We have 100% water saturation there. What happens when you start expelling water? Water saturation decreases, right? So it's lower and lower and lower because you're expelling water, right?